You're standing in the rain without an umbrella. Should you walk calmly and stay in the rain longer, or sprint like your life depends on it? This isn't just about staying dry, it's about geometry, velocity, and how the universe really loves to confuse you with simple questions. Today we're solving one of physics's most practical puzzles. Imagine you're at point A, and you need to get to point B. No umbrella, no jacket, just you, the rain, and a choice. If you walk, you'll spend more time in the rain. Each second, more drops land on your head. But if you run, you'll smash into raindrops from the side. Your chest, your legs, your face, they all become raindrop magnets. So what's the optimal strategy? Let's break it down. First, let's talk about rain falling from above, the rain that hits the top of your head. When you're standing completely still, raindrops hit you at a constant rate, let's say 4 drops per second. Now here's the weird part. When you start walking, the same number of drops still hits your head per second. Why? Because as you move out of the path of one raindrop, you immediately move into the path of another one. Even if you sprint at full speed, the rain from above hits you at the same rate, 4 drops per second, always. Here's a mind trick. Imagine the raindrops are frozen in space, and you are moving upward through them. This is where geometry saves us. There's a shape called a parallelepiped, basically a 3D parallelogram. No matter how much you tilt a parallelepiped, its volume stays the same. So no matter how fast you move horizontally, the same volume of rain hits your head each second. Top rain is constant, that part is solved. But here's where it gets interesting. If you're standing completely still, you don't get hit by an NY rain from the side. The moment you start moving forward, raindrops start hitting your chest, your face, your legs. Think of your body as a vertical wall moving through space. Every raindrop in your path, you're going to hit it. It's like a snowplow clearing a road. Whether the plow moves slowly or quickly, it clears the same amount of snow over the same distance. Your body has a capture zone in front of you. The total rain you'll hit depends on the distance you travel, not how fast you go. From point A to point B, there's a fixed volume of rain hanging in the air. You're going to collide with all of it, no matter your speed. The side wetness formula is simple. Rain density times your body's frontal area times the distance traveled. Walk or run, the side rain stays the same. So now we have 2 sources of wetness, top rain and side rain. Total wetness equals top rain per second times how long you're in the rain, plus side rain per meter times the distance you travel. The first part depends on time. The second part depends on distance. Since the side rain is fixed by distance, the only thing you can control is the time you spend in the rain. And how do you minimize time? By running as fast as possible. The answer becomes obvious. Speed minimizes your exposure to top rain. But wait, what if the rain isn't falling straight down? What if there's wind? In real life, rain almost never falls perfectly vertically. Wind pushes it at an angle. Now the rain has both a vertical component and a horizontal component. Here's the trick. If you run in the direction the rain is coming from, you reduce the relative speed between you and the raindrops. But if you run in the direction the rain is going, you increase the relative speed and get even wetter. The optimal angle? Lean forward into the rain and run as fast as possible. You want to match your body's angle with the rain's trajectory to minimize your cross-sectional area. A vertical body catches more rain than a tilted one. It's all about surface area. Of course, running in the rain introduces other problems. Puddles, slippery sidewalks, face planting. Physics says run fast. Biology says don't break your ankle. And what about your clothes? Different fabrics absorb water differently. A cotton t-shirt becomes a sponge. A waterproof jacket laughs in the face of rain. And let's not forget wind strong enough to turn your umbrella into a parachute. The real world is messy, but the physics? The physics is clean. This question is so famous that Mythbusters actually tested it. They wore identical absorptive suits, walked and ran the same distance, then measured water absorption. The result? The runner absorbed less water. The math was right. Speed wins. Science wins. Your dry socks win. Let's get weird. What if you were running through rain on another planet? On Jupiter, rain is made of liquid helium, and it falls sideways at 400 miles per hour. On Titan, Saturn's moon, methane rain falls in slow motion because of low gravity. Droplets the size of your head drift lazily downward. On Venus, it rains sulfuric acid, but the atmosphere is so hot the rain evaporates before it hits the ground. So technically, you could walk or run. You're not getting wet either way. Back on Earth, every year about 505,000 cubic kilometers of water falls from the sky. That's enough to fill 200 billion Olympic swimming pools. And you're worried about staying dry while running to your car. Every raindrop that hits you is part of a cycle billions of years old. That water has been inside clouds, oceans, rivers, dinosaurs, ancient humans, and now it's falling on your head while you check your phone. The universe doesn't care if you walk or run. But physics does, and physics says, run. So next time you're caught in a downpour, remember this. The universe is governed by rules, elegant mathematical rules. And sometimes those rules give you permission to sprint like a maniac through a parking lot. Because science isn't just about understanding the universe. It's about staying dry. Now get out there and run. But before you go, let's appreciate something beautiful. That raindrop hitting your nose right now? It has a story. Maybe it was once inside a T-Rex, or frozen in a glacier for 10,000 years. Water molecules don't disappear. They just keep moving, keep cycling, keep falling. So when you're running through the rain, you're running through history. Humans have been doing this exact calculation for millennia. Do I walk or run? Cavemen didn't have equations, but they had instinct. And instinct said, move fast. Turns out their instinct was right. Physics just proved what survival already knew. We evolved to minimize danger. Getting soaked in freezing rain? That's danger. Hypothermia doesn't care about your philosophical stance on walking versus running. So your body learned less water equals better odds. Today we have weather apps and waterproof jackets. The stakes are lower. But the physics? Speed still minimizes wetness. Math still wins. So take a deep breath and run like the universe is watching. Because somewhere in the grand mathematics of existence, staying dry matters.